Okay, welcome to part 2 of this problem. In this problem, we are going to go over the algorithm for solving this problem. So as a very quick review, we're dealing with a bunch of forces in the three-dimensional space, and we ultimately want to write a script that could take all of these forces and figure out the resultant force. So in the previous part, the video right before this one, we went over the problem statement. We figured out that we can represent forces with this equation right here. We talked about the unit vector lambda, and then ultimately how we could figure out what the components of the resultant force are. So in this video, I want to look at the algorithm, how we are going to define the algorithm and what our code should be doing in Python to be able to solve this problem. To start off, remember, when we're trying to figure out the resultant of a bunch of forces, what we ultimately need to do is we need to look at each one of those forces, break those forces down into the x, y, and z components, and then sum all the x components, the y components, and the z components, and that will give us the resultants, x, y, and z components, respectively. Now, to start off with our algorithm, the very first thing we want to do is define our input. So what input in this problem do we have, and what do we need to define in order for this script to work? So the very first thing, if you remember from the last video, is that all these lines of actions for each one of these forces goes through this point A naught. So that I'm going to call the origin point or the particle point, right? We need to know where this point is because all of these forces are interacting on that point, or the line of action for all of those forces are going through that origin. So the very first thing I want to do is I want to have a variable that defines the origin for that point. And I'm going to, in code, make this a tuple. Now, if you don't know what a tuple is, it's simply a data structure in code that we can just put in a bunch of values, like a set amount of values. So it's similar to like an array or a list. However, tuples are really cool because the order of the values matters, and a tuple can't be changed in length later on. So you can't just define a tuple first and then add on more values later, at least in Python. So what this tuple is going to have is it's going to have three different values. It's going to have x, y, and z, and these are going to be input values. So we are going to define the x, y, and z values in this tuple, and that is going to be set to our origin point. Again, if you don't know what a tuple is, don't worry. For now, just think of it as a data structure, a container, where we're going to input three values, x, y, and z. Now, the next thing we need to have is a list of all the ending points. And these ending points, if you look back at this diagram, they are going to be the ending points on each line of action. So here we have A1, here we have A2, here we have I, all the way up to AN. So we are going to need a list of these points because each point is going to represent a line of action for a particular force. And in the same way that we stored this value, the origin point, into a tuple, what we can ultimately do is, for this list of all ending points, what I'm going to do is I'm going to make sure each point, each coordinate point, is in a tuple, and this list is going to store all of those coordinates. So it's going to have A1, A2, A3, A4, AI, all the way up to AN. Now, along with those points, we also need a list that contains our force values, right? So each force that's acting on particle A naught, is going to have a value of some degree. And so we need to keep those forces also in a list so that we can iterate through them and figure out their x, y, and z components for later use. Okay, so very quickly, I already went over what a tuple is, but again, it's just a type of data structure that can hold values. So you can, in code, you can define a tuple by giving it a variable name, my tuple, for example, and we create a tuple by first starting with a open parentheses and having a closed parentheses at the end. And inside of those parentheses, we could have the values 7, 8, and 6. And so 7 represents the first item in that tuple, 8 represents the second, and 6 represents the third. I know it says 0, 1, 2, but again, that's because computers like counting from 0 as opposed to counting from 1. So again, tuples are really good because they are unchangeable, right? Once we've defined the coordinate for a particular point, we're not going to go in and add, a fourth element here. These points are always just going to have 3 values, the x, the y, and the z components of that force. So that is what a tuple is. So now once we've defined the input, once we have our origin point, a list of all those points, as well as a force list, the next thing we need to do is define variables to keep a running sum for the resultants components. Remember, we're summing all the components in the x, y, and z directions, and we're going to add it to the resultants x, y, and z components. So the next step after defining our input, we're going to create variables for rx, ry, and rz, and those are going to be initialized with the value 0, right? The resultant is going to start off with 0, but then we're going to iterate through each one of those forces, calculate the components, and then add them to either rx, ry, or rz. So once we've had those 3 variables defined, this is where the fun stuff starts. So this is going to be the heart of this algorithm. The idea for this problem is that we need to iterate through each one of the forces and determine its components, right? We need the x, y, and z components of every single force that's in our forces list. So we're going to start off by creating a for loop. Now, a for loop is just going to iterate through a particular list or a set number of values, and it's going to do a bunch of stuff for each force. So the things that we're iterating over is the force and the corresponding ending point. And so for each one of these forces, the very first thing we want to do is determine the lambda unit vector for that particular force or that particular line of action. And again, lambda is just defined by this equation. We need 3 different components, dx, dy, and dz. And once we have those 3 components, we could figure out this value d right here by taking the root sum square of dx, dy, and dz. And so remember, dx is going to be the x-coordinate of the ending point minus the x-coordinate of the starting point, and then the same thing for dy and dz, right? The ending minus the start, the ending minus the start. And so the idea here is that for each one of these 3 components, we are going to look at the ending point as well as our starting point. Well, what was our starting point? Here I said it was the origin point. So if we look back at the diagram here, let's look at this force right here. The ending point is going to be A2, and the starting point is going to be A0, which we've said is the origin point. So back in this for loop, when we're trying to figure out what lambda is for each one of those lines of actions, our ending point is going to be whatever point we're iterating over for that particular force, and our starting point is always going to be the origin, right? The origin, A0, for all of these different forces acting on particle A. Once we've figured out dx, dy, and dz, as well as the overall length d, we want to store the components of lambda in another tuple. And I'll show you how to do this in code, but the idea here is that you're just storing the values here into some data structure that we can use later on. So again, we're still in this for loop, and you can sort of see I've indented step 1, step 2, and step 3. But anyway, after step 1 happens in that loop, the next step is to determine the force components of that force. So again, we're still iterating over a particular force and a particular ending point. And because we already have lambda, we can figure out what fx, fy, and fz are. Well, how do we do that? We take the value of the force, multiply it by the x component of the lambda unit vector. And then we take for fy, same thing, we take f times the y component of lambda, and then for fz, take f times the z component of lambda. So once we've figured out these 3 different components, the last thing in that loop we need to do is we need to take that f of x component and we need to add it to the running sum into Rx, and we need to do the same thing for Ry and Rz. Remember, we've defined Rx, Ry, and Rz right before the loop, and they are going to be initialized as 0. But for every iteration of this loop, we're finding lambda, then finding the x, y, and z components of that force, and then we're adding that stuff to rx, ry, and rz. Okay, so once this for loop ends, once it's gone through every single force and every single ending point and added all those components to rx, ry, and rz, the last few things we need to do is, number one, we need to find the resultant's magnitude. And how do we do that? Well, we take the root sum square of whatever rx, ry, and rz are, and that gives us the magnitude of the resultant force. Now, in Python, in order to do things like squaring a number or taking the square root of something, we need to use the math library. So we'll have to import that in our script. And then because, scripting tends to work with a lot of significant figures, what we also need to do is we just need to round a lot of these values to something like 1 decimal point, because we don't need a rx component that is like 12 decimal points long. It's just unnecessary. So we're going to have to make sure that we round each of these values so that we can print it out to the console and it looks nice and understandable. So once we've done that, once we figure out the resultant's magnitude, we need to next figure out the orientation of that resultant force. And there's sort of two options, two ways that we can do that. We can either use the resultant's components, the rx, ry, and rz values that we found, or we can simply just use the lambda components, lambda x, lambda y, and lambda z. So in the case of the resultant's component, we know that at least in the x direction, cosine of theta x is rx over r. And of course, if you take the cosine inverse on both sides, you get this equation right here, which in Python, if we run this, we are going to get a value in radians. So we are going to have to convert from radians to degrees, and we can do that using this math library. And I'll show you how to do that in the next part. And similarly, we can do the same thing for theta y and theta z. That should say theta z, not theta y, so that should be theta z. We take the respective directions components, so rx, ry, or rz, divided by r, and then take the cosine inverse, and then you get these three values, and we're good. Or we can simply just use the lambda component. So we know that cosine of theta x is equal to lambda x, and if we just take the cosine inverse of lambda x, we get theta x. And so theta x and theta x, they are going to be equal. It's just, what preference do you have for doing this calculation? For our problem, I'm just going to stick with option 1. You could certainly do option 2 and compare the values. You'll notice that these three values are equal to these three values. And so it's really just, up to you which way you want to do it. But again, I'll stick with option 1. And you know what? That's pretty much it. Once we have theta x, theta y, and theta z, as well as the magnitude of r, that solves the problem. And what we'll do in code is we'll just print that information to the console and be good to go. So now that we understand the algorithm, let's jump into Python and start writing out our script in the next part. So see you guys then.